Testing. Okay, today's lecture will begin with geometry, and we'll be taking some of the material out of Chapter 11, Boas and Geller. So this will, towards the end of today's lecture, we're going to try to combine the ideas of functions and limits with geometry into analytic and coordinate geometry. First, what I'd like to do is mention about the homework assignment 4. This is a cleaner version of it. This is a tech document if you don't able to get the math easily recognizable. So this is composed of 10 different limit problems. The first problem is to show that the limit of sine x over x is equal to 1. This, of course, if you directly substitute x equals 0, you get 0 over 0, so there's something like L'Hopital's rule going on, but don't use L'Hopital's rule. What I'd like for you to use is some form of an epsilon delta proof to show that as x goes to 0, through both negative and positive values, that sine of x over x goes to 1. So as a hint, you might want to write this on a unit circle and then use some inequalities that come from inscribed polygons and triangles and circumscribe the definition of radian measure and some inequalities that come from geometry and trigonometry. So I can post some hints later on, but it's a very standard proof. Using the previous, you can directly show if given this limit, you can derive this limit. Now you don't have to do an epsilon delta here because it follows directly from the limit in problem 1. A not quite related limit, but if you change it around a little bit and look at the limit of sine of 1 over x as x goes to 0 to positive and negative values, show that it does not exist using an epsilon delta proof. And the way that goes, obviously, is it shows that it fails in the sense that if you prescribe an epsilon, there is no delta that you can find so that the function values remain within epsilon of the limit. So in other words, this function varies between minus 1 and 1, arbitrarily close to the origin, and that's what you need to incorporate using an epsilon delta argument to show that the limit does not exist. Another type of limit that you've probably seen before in calculus is the limit of the square root of x plus 1 minus square root of x. These both go to infinity, but infinity minus infinity is not defined, but in this particular case the limit is 0, and you just have to do some manipulations on this limit to show that, in fact, vanishes as x gets large. There's a nice key relationship of the Fibonacci numbers. The Fibonacci numbers, if you start with 1 and 1 and then add the previous 2, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, etc., 21. These numbers actually, amazingly, come from a sequence in closed form that involves square roots raised to the nth power. So what I want you to do is prove that the Fibonacci numbers actually satisfy this. You can do by substitution, first few values, but I want you to use induction to show that it's true for all n. Once you have that form, I want you to show that asymptotically the Fibonacci numbers look like a power r to the n times some constant c. So find the asymptotic behavior of the Fibonacci numbers. And actually, just by inspection, you can pretty much guess what things are. Another key problem is to show that pi can be written as a series. In fact, if you look at this reference, you can't click it on the PDF document, but if you go to the HTML, it'll take you there. There are 43 different infinite sum representations of pi. So for extra credit, you can derive as many of those series representations as you can. So if you take an alternating series of odd reciprocals of odd numbers, 1 minus a third plus a fifth, etc., get this series, it converges to pi in the limit. It's very slowly convergent. In fact, if you take away the alternating sign and make them all plus, the series diverges. And in fact, that's the seventh problem, is to show that this series diverges. Now, a series of positive terms diverging just means that as you let the finite sum of n get larger, the series is bigger than any positive number. So you can show that just by using some grouping, an argument based on grouping terms. Again, this is logarithmically divergent, and this, I guess, would be logarithmically convergent, very slowly converging series. Now, in number 8, there's a reference, again, you can pick this up on the HTML posting of the problems, called Archimedes the Numerical Analyst, where we talked about this before, where Archimedes inscribed polygons of 3, 6, 12, 24, 48, 96. He did bisection of a triangle inside a circle, and he actually was able to estimate pi using a 96-sided polygon. But in this reference, there are some extrapolation schemes, which you can read about, that can actually use these 6 numbers and kind of adding and subtracting in a certain way to come out with a 18 decimal approximation of pi, a pi accurate to 18 decimals. So I want you to just go through the details in steps 1 through 7 and show that you get 18 decimals accuracy for pi. Another limit, this is a continuity problem. The Heaviside function has a discontinuity at t equals 0, and show again using an epsilon delta proof that the limit does not exist. So that means given an epsilon, you cannot find a delta such that if you're within delta of 0, h is within epsilon of the limit. Finally, this is a nice little limit. Show that the limit of x to the x, as x goes to 0, equals 1 if you go through positive values. So that's again, I wouldn't just apply L'Hopital's, but you have to provide a fairly rigorous demonstration of this. Don't just put values in your calculator and say, see, they get close to 1. You need to be a little more precise than that. Okay, so that's a series of 10 limit problems. I posted them a little bit later, so they'll do a week from today, so you'll have the weekend, 7 days to do that. The next chapter in the Boas and Geller that I want to cover is chapter 11. This is on plane geometry. And what I'd like to do is start off with the classical versions of geometry and then describe a little bit about the various differences in the types of geometry, how they differ. There's some nice little interactive applets in here that I'll show you how to work. There's a hyperbolic geometry, non-Euclidean geometry drawing applet, which is kind of cute. You can get sort of curvilinear triangles using this. I'll talk a little bit about the classical Riemannian geometry and the hyperbolic geometry. These were actually part and parcel of Einstein's theory of relativity. The Riemannian geometry is the generalization using arbitrary metrics, and that's very much tied to general relativity. A special metric giving rise to hyperbolic distances is in the special theory of relativity. I'll fix up the spelling errors here too. Just to show you that the breadth of this field, I have a link to the Journal of Algebraic Geometry, which is online from the American Math Society. And then I'll tie it back in to Descartes, who was the founder of analytic or coordinate geometry. More references and material can be found in Chapter 11, and the next homework assignment 5 will be taken from some problems in Chapter 11. So I'd just like to describe a little bit where, some of these geometry, some of these terms mean. So Euclidean geometry is a geometry where Euclid's fifth postulate holds. Now, Euclid's fifth postulate is the parallel postulate. And these are the 4 postulates that, or the original 4 of Euclid. A straight line segment can be drawn, joining any 2 points. A straight line segment can be extended indefinitely into a straight line. goes to infinity. A straight line segment in a circle can be drawn with the segment as the radius and one endpoint as the center. All right angles are congruent. Those four axioms or postulates form the basis of Euclid's first 28. But for the 29th postulate, he actually needed the parallel postulate. Now the parallel postulate is number 5. If two lines are drawn which intersect a third line in such a way that the sum of the inner angles is less than two right angles, so that means you actually have a triangle, then the two lines must intersect each other on that side. And let's see if there's a formal. Here's a more familiar. Given any straight line and a point not on it, there exists one and only one straight line that passes through that point and never intersects the line. So what that means is, and we'll draw here a little bit, what this means is if you have a line, let's use the line tool here. If you have a line segment and you have a point, P, not on the line, there is one and only one line segment that is parallel to this one. So let's actually move that so it goes through the point. Okay, so if you draw any other one, and let's change the color here. If I draw any other line segment passing through that point, these will intersect the lines. So this will intersect. This will intersect the line, obviously. And this is parallel. That is, it doesn't intersect. So the parallel postulate says, given a line of infinite extent and a point not on the line, there is one and only one parallel line. So in classical Euclidean geometry, there is only one parallel line. Now, if you change that to be 0 parallel lines or infinite number of parallel lines, you get different. This is a postulate. This is Euclid's 5th postulate. And it is not provable from the remaining. It's independent of the others. Which means you can have geometry with no parallel lines, with one parallel line or infinite number. And you get hyperbolic geometry and parabolic geometry and other types of geometries here. So if it's true or false, you can have different kinds of geometries. Okay. So Euclidean geometry is the classical geometry that we've grown up with. Now Euclidean geometry is axiomatic. In other words, there's no necessarily built-in distance. There's no notion of coordinates necessarily. And it's very axiomatic. When you add Euclidean geometry with the idea of coordinate systems, then you get something called analytic geometry. So if you have Euclidean geometry, plus coordinate systems, this is equal to analytic geometry. And this is the kind of geometry that you probably had in middle school. And this is due to René Descartes. Now there's a link at the very bottom. I had it somewhat out of order because I found it late. There's a link to René Descartes. He was a colorful fellow born in 1596 in France, died 1650 in Sweden. So, for example, he never got out of bed until like 11 o'clock every day, and was a kind of an interesting person. So this gives you a little bit of the historical color of René Descartes. But his contribution was to do exactly. He took two perpendicular lines and was able to describe any point in the plane, obviously with a distance x and a distance y and a coordinate. So this is very much like a map. So you can map the plane using these coordinate systems. Now, it's so automatic for us to do it this way that we forget that in the original geometry, there really wasn't this idea of a coordinate system. It was purely an axiomatic approach to geometry. Now, in 2 dimensions, Euclidean geometry was called plane geometry, and there's a link here that just defines plane geometry. Let's see, I believe I found this link. Yeah, this is actually an online course in plane geometry. So you can go through angles, similar triangles, polygons, congruency and proofs, all the way down through circles, polyhedrons, solids, spheres, and then there's a final exam here, and there's a test. So this is a nice little website. I haven't looked through the different things, but you can take a whole course on the web in plane geometry. In 3 dimensions, Euclidean geometry is called solid geometry, and this is a pretty nice site because you can go down here and actually build different things. So if you want to build a hexahedron or a dodecahedron, let's do that. So if you click on dodecahedron, it tells you, oh, this is a 12-sided figure. And you can view the model, and this gives you like a piece of paper and shows you how to build your own shape. So this is sort of the soccer ball shape here. What you do is you cut out this shape here on a piece of paper, and hopefully we have. But if you cut this shape out of a piece of paper, you can fold these things in and connect them to, and then it will all come out to this nice little 1, 2, 3, 4, 5. So there's 1, 2, 3, 4, 5, 6 on one side, 2, 3, 4, 5, 6. Oh, this came in on Zoom. That's good. So if you want to amaze your friends by building your own tetrahedrons, dodecahedrons, etc., this gives you lots of neat little icosahedrons, tetrahedrons, scribed in a hexahedron, etc. And so there's, I see the plates have, I believe, a nice little picture of, that picture here. The guy took a picture of a book. So this is kind of an online, this comes out of the library at Georgia Tech, so that must be a resource for teachers. Now, as an example of the kinds of theorems you have in plane geometry and not Cartesian or analytic geometry, I have a link here. The 3 links below are actually Java applets, which are kind of cool. So this gives you a bunch of theorems that come from Euclid himself. Let's go down here. This is on congruent triangles, straight lines bisecting the vertices, bisect the base, etc. So there's a lot of and you can see in here that there's no distances, coordinates, or anything else. It's all axiomatic. Now, to show an example of the kind of thing you can do on the web with this, if you click on Pascal's theorem, this downloads a Java applet. This is kind of a neat applet because you can play it like a movie and then you can also interact with it. Of course, everyone's downloading at the same time, so it'll be very slow. Okay, so as we finish loading this in here, let me pause so it's all the way down. Now this is a nice little app. This actually labels all these things and you can move things around. It won't do that. But this is the little play button down here. So if you start off with the play, we'll just go rewind this here. And that button's not working for some reason. So let me just, the first step is you put down 6 points. And then, well, actually, here's the statement here. If you have a hexagon, that means 6 straight line segments connecting A, B, C, D, and F. And now notice these are not collinear or even in order. It goes from A to B to C to D to E to F back to A again. Then the opposite sides intersect in 3 points, which are collinear. Pascal proved this when he was 16. So there's the 6 different line segments here. Now notice if you move any one of these, I think it suggests that you move drag C. So it's not moving very rapidly, but as you move it, you can get it continuously like this. So if you move it in one setting, you can get a one here. You can get everything from a hyperbola to a. Now this is weird. It's going very slowly here. So let me not worry about this. But you can play around with this applet, and it gives you a very dramatic rendition of this film in plane geometry. There's another film. Let me download this before you all. Right. Okay, this is a proof that if you take 6 lines, well, if you take A, B, C, D, and F, and all of these lines lie on a conic circle, for example, circle, then the lines A, B, B, E, etc. all lie on one point. So if we move this around, it actually constructs it here. Let's go rewind. What's that? Don't know why. Okay, so if we move this forward one step at a time, we're putting in 6 points, C, 4. When you connect these, if they're on opposite sides of a circle, then connect these. Yeah, this is very slow. Just rewind it. I won't even go through the third. This is another theorem for a triangle. So there are Java applets that actually let you manipulate. Yeah, this is kind of a fun theorem because you can move this point around and generally get different figures here. But again, this is not going to record well, so I'll let you go ahead and investigate them and play them. Now, Euclidean geometry is with the parallel postulate, if we apply a different idea of distance, so we know that with the Cartesian coordinate system, the normal distance is, of course, in two dimensions. If we have a point here and a point here, and this is x1, y1, x2, y2, the normal distance d is just the square root by the Pythagorean theorem of the difference in x's and the difference of the y. Well, when special relativity came in, they actually defined a slightly different add. So they have three space points, x, y, z, and time, and they defined the distance as the normal spatial part, x1 minus x2 squared, y1 minus y2 squared, z1 minus z2 squared. But then they subtracted t1 minus t2 squared. So it's this minus sign that makes all the difference in the world. This is analogous to putting the normal Euclidean distance metric on the points x, y, time along imaginary, because then if you square it, you get minus. So it turns out that this idea of x, y, z, and distance and time is invariant. So this is the Lorentz transformation says that this distance or this metric is invariant. Now, if you make it even more general, this is a discussion on the non-mathematician, where it says we have a unification of coordinates, we have trigonometry and conic sections, at least a pair of almost good. It's a straight line distance because that would actually go right through the interior surface and the connections which are all the way around the sphere and connect it. So think of it because the Earth's crust. So you have to fly along the surface, and if you're an airplane, you're obviously trying to save gas, take the shortest path. And what do you mean? Well, the shortest path, you would integrate along this distance in 2 dimensions, and you would get a distance for this path and all other paths, and you define the distance between these 2 points as the integral of the arc length along this path. But that's a certain metric or distance that you define. So this, if you're on coordinates, so this is on a sphere, you can ask the question, what is the distance between 2 points? And what we mean by distance is actually the shortest distance, because any other distance is not unique. And this is often referred to as a geodesic. So it's geodesic. So it's the part of the great circle. If you took these 2 points and take a plane that passes through the center of the Earth and those 2 points, and then take the intersection, let's draw that again. So it's actually, there's a better circle. And if I probably can do an elliptical circle. So if you take a plane and slice through your sphere through 2 points in the center and here, and then look at the plane that is how this arc is cut through here, then the part of the great arc circle that connects these 2 points will be the geodesic. So there is no other distance that's any shorter than taking the plane that passes through the center of the Earth, these 2 points. Now, it also should be clear that you could go one other way, right? You could also travel the back end and come around. So it's like, how do you fly from Los Angeles to New York? Well, you can go the long way around the Earth, or you can go the short way. So this idea of distances combined with geometry gives you the idea of a Riemannian geometry. So the general notion of a distance, which is known in mathematics as induced by a metric, plus geometry, this gives you the notion of Riemannian geometry. Now, this is extremely complicated and very complex subject because it really is analysis of curved surfaces. So this is geometry on curved surfaces. And in more general, what are called manifolds. Okay, so this we'll come back to later. I'd like to look at this in a later lecture, because right now we're just focusing on Euclidean geometry. But if you take your idea and concept of geometry, add on to it a more general notion of distance that's valid for curved surfaces, you can do geometry on curved surfaces, the Riemannian geometry. Now, the Riemannian geometry in all its full form is what really feeds into general relativity, because that defines geodesics. It turns out that light rays travel in the shortest distance through space, and they follow, and they're bent because they're following the curvature of space. And space bending and the fact of gravity are indistinguishable. And in fact, you can think of gravity as, or mass as being responsible for curving or warping space. And I'm sure you've seen all these wonderful pictures of, here we are in flat space. Then if you stick like a sun or some body in here, then there's these things that come out like this. And in the limit, I mean, if you have something really huge, so light rays, if they travel along here, don't follow. If they pass near a body, they go along straight, and then they're kind of warped, and then they go straight again. So to us outside here, the light rays appear to bend, but they really are traveling along the shortest distance in this curved space. Now, because we don't live in two-dimensional space, in three-dimensional space, it's hard for us to visualize 3D space curving. But if we were in 2D, the curvature would be obvious to us in higher dimensions as a warping or a folding. It's like take a sheet of rubber and put a marble in there, and the rubber will kind of deform the surface a little bit, and that's exactly what objects with mass do to space. So if you look at general relativity, which really links gravity with curvature of space, and that's exactly the picture here. We don't live in a flat dimensional space where there's just a sun here with orbiting bodies traveling around, but we live in a more complex geometry. Now, here's an example I found of applying not the Pythagorean, the standard metric. But this allows you to draw. Okay, so here's an interesting idea. If you have the hyperbolic model, this is a Poincare model that's actually mentioned in Chapter 11 of Boas and Geller. If you draw a line segment through the center, it looks just like a standard line segment. So when you're near the boundary and you're connecting 2 points, the points are curved. So you could think of this as looking at the top of a basketball and you're drawing straight lines through the basketball, but the intersections are curved along the surface. So if I were to draw a triangle connecting this point, and these 2 points, you can see that the triangle is curved. And clearly these interior angles don't necessarily have to add up. They can be very sharp. They could add up to less than 180 degrees. So if we clear this, we can even have a 4-sided figure. Right? So again, what this means is, according to this particular metric, this hyperbolic geometry metric, and this allows you to move, and this. So this is a very nice app. It really is kind of a lengthy process to get your intuition going in non-Euclidean spaces because things don't quite behave the way you think. So there's a link here to the hyperbolic geometry, which you can follow. Now this is actually coming from University of Minnesota, that remains of their geometry center. So this has an exhibit of various Euclidean and non-Euclidean geometries, but there's a link to special relativity. And where you see the Dumpata, this says that the distance between 2 points in R2 and time, it's not the sum of squares, but the time is there as a difference of squares. Yeah, I got clearing up an answer here. Okay, I was not able to get that particular applet downloaded. I just wanted to show one other link, and that's to the Journal of Algebraic Geometry. This is one of the new breed in just linking them with geometry. So you have, for example, you can have equations which describe conics. So we all know that if you have an equation like x squared plus y squared equals 1, this describes what? This describes a unit circle. If you have x squared minus y squared equal 1, that's a hyperbola, right? So this would be plus or minus 1. So it should probably look like that, with asymptotes y equals x and minus x. And if you have y equals x squared, that's a parabola. So these are the so-called conic sections, because if you take a cylinder, you can intersect it with the plane and get circles and parabolas, etc. Now, relating these polynomial equations to surfaces and curves, in more general applications, gives you a really interesting subject about the properties of equations, how they relate to the geometrical properties of solutions of these equations. So what are the geometrical properties of solutions? As curves or graphs. This gives rise to a subject called algebraic geometry. And it's a way of blending together functions, algebra, and geometry in a very deep way. And there's actually a journal online, and you can click on these and actually look at articles. So if you want to, let's see, most recent issue, click that. And then there's a way to download articles in PDF form. So if you want recovering planes from the bitangents or rational curves on projective hypersurfaces, just click on the PDF file and ask you for a password. That's clever. Guess you have to be an authorized user. But I think you can get the abstract references and article information without being signed up. So this is a new experiment actually in disseminating mathematics. So this is with references. This gives you a sort of abstract and a summary, contact information for the author, basic information that you would need. So there's a lot of terminology in algebraic geometry, and I'm not in that area, so it probably makes as much sense to you as to me. But you can just go through some of the issues there and get an idea of what the subject is about. As I mentioned, the sort of progression that occurred here was Euclid way back in 250 BC. Pretty much remained a steady stream up until Descartes, which was in 1700s, let's say 1600s, where we had Cartesian coordinates, and the word Cartesian is derived from Descartes. Then this is what we call analytic geometry. And then as soon as people started looking at discussions of functions and their graphs and their properties, like curvature of lines and, solutions of equations and the locus of solutions of equations, etc., derived into an algebraic geometry in the 1700s to current. And then we had then we added the idea of Riemannian geometry, which is adding metrics, generalized notions of distance on curved spaces. And then we have the geometry unfolding into just all kinds of subspecies. There are algebraic geometry, differential geometry, and all the various species of Euclidean, non-Euclidean, etc. So about this point, people discovered that these non-traditional geometries had a very important use, and the non-Euclidean, the hyperbolic, was used in special relativity, and this is early 1900s. And the more general would be in the general relativity in the 1930s. Well, actually, I think it came a little earlier, early 1900s. So physicists have taken to using the language of mathematics, manifolds, differential forms, etc., to describe physics in curved space, and that all very much uses the language and the notions of Riemannian geometry. So if you pick up an article in theoretical physics that has to do with solving things like Einstein space-time field equations. It'll all be couched in the language of mathematics and Riemannian geometry. So what we understand is Euclidean or solid or plane geometry. So there's plane and solid. These are what fit our R2 and R3. But if you add in more complexity to them, like time for special relativity, or curvature, as in general relativity, Riemannian geometry, you get much more complexity. So at this point, I think I'll end. The next lecture was going to be covering part 2 of geometry, and I think what I'd like to do is find some nice references on non-Euclidean geometry and sort of how it played a role more currently, and then just go through some of the terminology and some of the tools. Let me just remind you that the homework assignment is going to be number 4, and that's due a week from today, so it's the 25th of February. There's a PDF file here, and you can pick up an HTML version. The only advantage of the HTML version is that there are a couple of links there so that you might pick up directly in case you can't grab them from the PDF page. Okay, so that's going to be it.